We're now going to quickly summarize the results of our work with all the eigenvalues and eigenvector calculations that we've done. The eigenequation, or the eigenvalue-eigenvector equation, states that for special or characteristic, something that's special about those directions combined with A, directions V, A simply scales, again, or flips, but it's a scalar multiple of vectors parallel to V. So for some special directions, all A does is scalar multiply them. It has that effect. Most vectors, it'll do some shifting, it'll rotate, it'll do something else, but for some characteristic directions, that's all we get. And so by this specific value, lambda is the ingredient after that. Our goal in the previous videos was to identify, well, given A, which vectors and by how much, and we found two conditions that led us to those answers. We find the eigenvalues by shifting this around, and if you want, honestly, I just memorize this, and then I do the two-line derivation to get down to this. But you can also memorize these on their own, whatever makes more sense for you. When we move this lambda v to the other side and slide in an identity matrix so that we're comparing matrices and matrices, we end up with a condition that for lambda to be an eigenvalue, we have to have a degenerate matrix or a non-invertible matrix here. And as we've seen, a test for that is that the determinant is 0. That's equivalent to saying A minus lambda I is not invertible. Then once we have those lambda values, we can sub that in. We get now a matrix. So this is an equation with matrices and vectors. This is an equation with a matrix, but then we take a determinant, so it gets down to a scalar. Here we have a matrix times a vector equals a 0 vector. And for any given value of lambda, we know all the ingredients here. So this becomes a known matrix, and we can solve for V. Again, I just want to remind you that the eigenvectors are a basis for a subspace. So basis is like one representative. And it means that if you and your colleague in the class are doing this work finding eigenvectors, you might have found, say, 3, 1, they might have found 6, 2, and guess what? You're both right. Those are both eigenvectors. We often use the terminology with this is an eigenvector of A, so it's one of many possible eigenvectors. And one of the things that covers is the fact that anything parallel will be also an eigenvector. And of course, because we're in a linear algebra class, we should prove that. If we're told that V is an eigenvector, so it satisfies this, then it's an eigenvector of A, then what we're allowed to do is multiply both sides by some constant. Lambda V for some K, some real K value. We can just multiply both sides by scalars, that's fine. Then the wonderful thing about scalars and matrices is we can invert the order if we want. So now we have the K multiplying the vector first, doesn't change anything. And here, let's multiply the lambda and the K, we know we can do that. That's like 2 times 3 times a vector, it's the same as 3 times 2 times a vector. And where does that get us? Oh, that gets to our conclusion. Because this vector times A is equal to this vector times lambda, that means that K times that vector is also an eigenvector. Why? Because it satisfies the eigenvector equation. Now, if we think about the scaling interpretation of eigenvalues and eigenvectors, let's just do this in 3D, just to give us some context here. Say, for example, we found that the vector, I'm just going to call it ABC, is an eigenvector. There's an eigenvector for A with, say, lambda equals 2. Make our lambda look like lambda. There we go, with our lambda equals 2. We'll draw our vector on here like so. Let's make that our vector V. So what this says from the eigenvalue condition is that if that's my vector V, then I know for sure that A times V is going to be equal to 2v's. It's going to double the length. Well, because the transform's linear, if we had a vector pointing in the opposite direction, as long as it's along this line, let's call that w, but parallel to v, then guess what? When we multiply it by a, it is going to get multiplied or scaled by 2. So a times w. So whether you pick v as your eigenvector or something parallel to it, it doesn't matter. It's still an eigenvector, and everything in that line is going to get scaled by the same amount. So the eigenvalue will be consistent, and any vector along that line is going to be a corresponding eigenvector. And that completes our introduction to the basic calculations and ideas behind eigenvectors and eigenvalues.